All right, so when the currents are in the same direction, magnetic forces are going to be pointing towards the other wire. Okay, so which means that the wires are going to be attracted to each other. All right, so the magnetic field due to the second wire is going to be pointing in the downward direction. So what that means is, once again, let's just change the notation a little bit. Okay, so this is the force acting on the second wire due to the first one, and this is the force acting on the first wire due to the magnetic field of the second one. So notice that they're pointing towards each other. Okay, so this is how you come up with the formula mathematically. This is the mathematical expression for the concept that we've been discussing. All right, so when the currents are in the same direction, there's going to be a force of attraction because of the magnetic forces directed towards the wires. When the currents are in opposite directions, the magnetic forces will repel, so which means that the wires will repel. Okay, so pick out the best answer whenever you're ready. Just jump in.
Repel. B.
All right, those of you guys who said B, give yourselves 5 points. Those of you guys who picked B, give yourselves 2 points for that one. Okay, let's talk about the solenoid briefly. Looks like this. We'll have a little bit of a conceptual discussion regarding the solenoid. So the current is moving this direction, so it's going to set up a magnetic field just going around. All right, so line up your thumb in the direction of the current. Your fingers will give you the direction of the magnetic fields. All right, so in this case, the current is going into the page here, it's coming out of the page, going into the page. So which means that the magnetic field lines will wrap themselves around in this direction. Okay, I'm not going to do the derivation right now, but I want you to take a look at this. Okay, so according to the formula for the solenoid, here's what we end up getting. The solenoid formula. Okay, do I have the solenoid formula? Yeah, of course I do have the solenoid formula right here. Okay, guys, here's your solenoid, here's the formula. Okay, what this formula gives you is the strength of the magnetic field inside the solenoid, right in the middle, the strength of the magnetic field inside the solenoid. It depends on the strength of the current. That's it. That's a simple enough fact. Okay, so that formula gives you the strength of the magnetic field on the inside. And if you're looking at the formula, notice that the strength of the magnetic field on the inside has to be uniform because it does not depend on in radial distance. Okay, the magnetic field here is the same as the magnetic field here. Strength of the magnetic field is going to be uniform inside the solenoid. That's what the formula says. The strength of the magnetic field on the inside only depends on the strength of the current. That's the amount of current that you have inside the loops. All right, so the question is, how's that possible? All right, is the strength of the magnetic field inside the loop constant? Yes or no? What do you guys think? All right, this is a discussion question. This is the sort of stuff that hits you on the conceptual portion of the test that you guys kind of miss all the time. Stuff that I'm looking at it, I'm realizing all of a sudden that the strength of the magnetic field inside the loop is a constant. Is it constant inside the solenoid? Yes or no?
Wouldn't think it would be because you'd think it would be stronger closest to the wires, right? So it'd be weakest right through the center.
Okay, Nathan, I'm gonna give you 5 points. The only thing you have to do is just look at the placement of the lines, guys. These are your magnetic field lines. Okay, right within this region, it looks like, I mean, I'm talking about within this region. If you're looking at right at the center, it looks like it's uniform. But towards the edges, notice that the strength of the magnetic field becomes weaker because notice that these lines are diverging from each other right here. Okay. Now, the strength of the magnetic field is going to be uniform only at the center of this small region that you're looking at. Okay. I don't know what the placement of this region is, but that's the small region. Or you can make the assumption that right here it is constant. And when you start to come towards the edges, not so much because the lines are diverging. Okay. So what that means is this formula is correct, assuming that you have an infinite solenoid. Okay, so this formula that we were just discussing is correct, assuming that it's an infinite solenoid, or you're only looking at the very center of it. Okay, so you're looking at it right at the center, the formula holds. Towards the edges, this thing is just going to go to hell. So at the fundamental physics level, just for you guys, this is literally baby physics for the technically minded. This is for you guys. The underlying assumption is that this is an infinite solenoid. In reality, this sort of assumption only holds true within a very small region inside the solenoid, so right at the center. All right, so once you make that distinction, that we're on the same page. When you take a solenoid like this, assuming that this is an infinite solenoid, everything works out fine. And then you can take a solenoid and turn it into a donut. And this is still a solenoid, turn it into a donut. It's called a toroid under the circumstances. All right. When you have a toroid, the formula is still going to look the same. All right. So when you have a toroid, the formula looks the same. I got to make room here. Everything is fine. Everything is fine. All right. And then one more formula. We have to squeeze one more formula into this mix. All right. So just move it up, make it slightly smaller. And then we need to get a toroid formula. Okay. So toroid is a donut solenoid. All right, so you grab the solenoid and then turn it into a donut. All right, so just grab that. All right, I messed it up. Okay, so it's known as a toroid solenoid. All right, now we will be interested in the strength of the magnetic field on the inside. Strength of the magnetic field on the inside. Let me check to see what happens. All right, if the current is moving in this direction. All right, so if the current is moving in that direction, the magnetic field is going to wrap itself around in that fashion. Okay. This is the same formula that we will get to use for that. Formulas are identical. Oh my God, I'm getting so annoyed. We got disconnected again. Okay, so given the fact that the formulas are identical, it's not going to work. We got to wait. Let's stop it. Get out of here. Let's get a new number. Okay, so okay, guys, given the fact that we're using the same formula for this case, it's the same as the solenoid formula. Solenoid formula is right here. Toroid formula is here. Solenoid and toroid, they're the same, except you grab a solenoid and then just turn it into a donut. It becomes a toroid. Okay, so you know that the strength of the magnetic field on the inside is going to be constant in the case of a solenoid. Can you make the same argument in the case of a toroid? Yes or no? Can you make the same argument in the case of a toroid? What do you guys think?
No.
Okay, Ian, you said no. Why did you say no? Okay, so the strength of the magnetic field inside a solenoid is constant. Inside a toroid, can you make the same argument?
Wait, that it is constant?
Okay, so it is constant. Oof. Man, sometimes technology just works so well, and sometimes it just doesn't want to. Okay, so here it's constant. In the case of a solenoid, it's constant. We discussed that already. Okay, and can you make the same argument regarding the toroid? Can you also say that inside the toroid, the strength of the magnetic field also constant?
Yeah.
Okay. Of course, you will make the same argument because we got the same formulas, right? Okay. Obviously, the strength of the magnetic field here only depends on the current. The strength of the magnetic field also depends on the current. And I'm kind of forcing you to come up with the same conclusion, obviously, because I like to do that. If I were not a physicist, I would be a really good politician or a con man, I suppose, because I like tricking people. Guys, you can't use the same logic here because as it so happens, the strength of the magnetic field is not going to be the same inside a toroid. Case in point. All right, so the strength of the magnetic field here. Man, I wish I had some kind of a second pen for this one. R1, locating this, and R2, locating the bigger. You just look at the green circles. R2 are not going to be the same. All right, so the strength of the magnetic field in the inner radius is going to be stronger than the magnetic field in the outer radius. So the question is why?
Why is your space farther apart on the outer radius?
Okay, Nathan, explain again. I think you hit on the idea. What's the reason?
Since the wires are spaced farther apart on the outer radius, there's well, that's related somehow.
Okay, I'm going to give you 10 points for that one. In case there's a test question, I'm hoping that some of you guys will remember that because you don't have as many turns, okay, as you're radially moving away from the center. Okay, so let me just make that point clear. Okay, what time is it now? All right, we got 7 minutes to go. Okay, mathematically, let me just explain it once, And then one of the things that I'm trying to get is the mathematical explanations. Wow, this is weird. Okay, very good. This is not the best way to go most of the time. I don't know why a lot of physicists like to explain stuff mathematically and then it falls short somehow. Okay, here's where the math works really well, and here's the reason why it's going to fall short. Okay, n here is the number of turns per unit length. All right, the length that you're looking at, this is the total length of the solenoid. In this case, the total length of the solenoid is going to be the circumference. All right, so that happens to be the circumference. Okay, so r in this case is going to refer to the distance from the center to the magnetic field lines that we're looking at. So just remember, r is the radial distance to the location where you're measuring the strength of the magnetic field. Okay, so we will rewrite this. So it's going to be n divided by L, which happens to be 2 pi r, v naught times I. Okay, that's it. So just write it out. Total number of turns, v naught times the current divided by 2 pi r. Okay, which means that at a larger or longer radial distance, the strength of the magnetic field is going to be smaller. So the magnetic field right at this location is going to be stronger than a magnetic field further away. That's what it means. All right, so larger the distance with respect to the center is, the smaller the strength of the magnetic field becomes. So the magnetic field strength is going to be inversely proportional to the radial distance. All right, Nathan provided the best explanation. And in case there's a test question, this is what I'm looking for. Okay, what I'm looking for is the fact that notice that when you are moving away from the inner radius, which is from this edge towards the larger edge, the density of the wires become less. All right, so which means the wires start to get further apart. Okay, and when the wires start to get further apart, the circumference is going to change. All right, as the circumference changes, the larger the circumference is, the number of turns become less. Okay, so the number of wires responsible for the magnetic field, number density of the wires will become smaller as a result, and the strength of the magnetic field further away from this center of the circle is going to diminish the strength of the magnetic field. Okay, so as you can see from here, once again, look at the density of number density of the wires, number of turns per unit length. Okay, they're right next to each other. Okay, so the contribution of these wires to the strength of the magnetic field on the inside is going to be stronger. And now take a look at the number density of these wires. Notice that there's a lot of space between the wires. So within this region, you've got 3 wires contributing to the magnetic field. And if I isolate the same amount of region here, you can barely have 2 wires contributing to the strength of the magnetic field. So this is going to have a much stronger contribution in this direction than this one. That's what it means.